was the last lecture. In the new lectures, we will be discussing about the various type of the possible electrophilic substitution reaction for benzene for the other aromatic compounds. In fact, benzene is the representative of all the aromatic compounds. So we will only be discussing about the reactions of benzene here. You can see that benzene can undergo sulfonation, alkylation, acylation, nitration, halogenation. You are all familiar with all these kind of the reactions. But the important thing is in this course, we will be trying our best to discuss about the detailed mechanism, the various steps, and then we will be going ahead with some more new things about these reactions, the energy profile. So one by one we will be discussing about these reactions. So on slide number 10 you can see that generally we represents the electrophilic reactions. Electrophile is represented by E plus. So there's a general trend that E plus, it means that an electrophile. So in the last lecture I have received few of your questions where you were discussing about attacking of the electrophile. This is quite unusual for an organic chemist by saying that electrophile is going to attack on something. Being an organic chemist, you cannot say this. Electrophile is an electron deficient. It can never attack on anything. In fact, it is being attacked by something, and that something means nucleophile. So electrophile, being an electron deficient, is always attacked by a nucleophile because this is electron deficient center. In other words, you can say that how is it possible that proton is going to attack electron? In fact, electron has to come and to attack on the proton, being the lighter particle. So electron always going to attack the slide number 12 electrophile of the PowerPoint lecture that I have shared with you last time. You can see that the benzene is being reacted with the hydrogen in presence of the iron and nickel, and we are getting the two one of the bond is being hydrogenated, and we are left with the two isolated double bonds in the 6-member ring. So you can see that if you are trying to hydrogenate these two isolated double bonds, they definitely undergo the addition reactions, but that addition reactions will be quite different from the type of the addition reactions where we have the two double bond conjugation. Hydrogenation of the two conjugated double bond is a bit difficult than the hydrogenation of the mono already double shared bond. The mechanism of the Birch reduction with you, but I want to add something to the Birch reduction, because whenever you're talking, whenever we have an electron donating group attached to the ring, and then the Birch reduction, that will be different. If a benzene ring have an electron donating group, that will have a different reactions than the type of the substrate where we have an electron withdrawing group attached to the benzene ring. So these two have two different type of the normal benzene. There will be no problem discussing the Birch reduction. I have already shared with you the mechanism of that reaction. But just take an example where we have a monosubstituted benzene ring is there as a substrate. That monosubstituted substituent could be an electron donating group, that could be electron withdrawing group. So here in this example, that this picture that I have shared with you right now, you can see that the toluene group, the methyl group is present on the benzene ring, which is an electron donating group. Similarly, the NH2 group, that is also electron donating group. And in both of, what about the nitro group? Nitro group is an electron withdrawing group. And similarly, this acetyl group is also an electron withdrawing group. So the first two examples, the two electron donating groups are there attached to the benzene ring, and in the last two examples we have the electron withdrawing groups. So in the first two examples you can see that the type of the product for the Birch reduction is a bit different from the situations where we have an electron withdrawing group. I mean the last two examples. The last two examples, they are different from the first two examples. Why? Because if you have the electron donating group attached to the benzene ring, you can see that there will be the bond will be directly attached to the carbon, that is where the substituent is attached. You can see in the first two examples, the double bond is there at the carbon where the substituent is attached. But this is not the case in the last two examples. You can see when the electron withdrawing group is there, what would happen, what will be the situations. You would not have the double bond attached to the carbon that is attached to the substituent. In fact, that it will be away from the carbon of the substituent. I think is it one by one we will have the mechanism of both these reactions. You can see that in the first reaction there is an attack of the electron. That electron is coming from the sodium or any other metal, could be a lithium or sodium. So this free electron or this one electron is coming and is going to attack on the carbon away from this from that carbon which is attached to the substituent, I mean the alpha carbon. So if that is attack on that carbon, what would happen? The electron, the single-headed electron is now moving on the other side, and then we are having that carbanion. And now this carbanion is abstracting a proton from the tertiary butanol, which is an alcohol. And then you are getting that two double bonds, two parallel double bonds. But one of the double bond is attached to that carbon, which is where the substituent is already attached. And next, what happened? The electron is going to attack at one of the hydrogen, and then resulting into another carbanion, and carbanion again abstract proton from the butanol, tertiary butyl alcohol. And then we're getting that end product E. So just look at the other example where we have an electron withdrawing group attached to the benzene ring. Here in this case, the electron which is coming from the sodium or from the lithium, that electron is going to attack on the carbon where the substituent is attached. That is directly attacking on that carbon where the substituent is attached. So you can see the flow of electrons. There's a half-headed arrow that is moving the electron forward, and then ultimately we will have this carbanion B, the product B. You can see that here the two double bonds, they are produced. They are parallel though, as the per requirement of the Birch reduction, but parallel, but they are in away from that carbon where the substituent is attached. And now this the next step, you already know that it is abstracting a proton from the tertiary butyl alcohol, and then we will have the product C, where there is already a free radical existing. So after abstracting another electron, this free radical will be changing into another carbanion, which will abstract proton from the tertiary butyl alcohol. Here you can see that they have showed the two equivalent structures, resonating structures, for showing by D. It means that they have the same, because there is a electron sink existing. That's why they can also, the electron can also shift to the towards oxygen. So we will have both of the form coexisting in this reactions, but ultimately we will have that product E, right? So we can have that product A, or we can have the product R. So when we will have, if we are trying, if we are using the alkyl halide, then we will be having the product F. But if we are using the tertiary butyl alcohol only, then we will be having product E. So I don't think there's any problem in understanding both of these two concepts. This, I think it's very clear now. Let me know if you didn't pick up. Next is the halogenation of aromatic compounds. So you can ask that why I'm saying that the benzene doesn't undergo the halogenation. Benzene undergo. In fact, I didn't say this. I'm saying that benzene can undergo halogenation, but that will not be addition reaction. As you saw in the case of cyclohexene, where we have the same sort of the product where a chlorine ring was attached to the cyclohexane. More or less the same sort of the things are happening in benzene, but their mechanistic pathway is different, because in benzene ring we have the substitution reactions in presence of the Lewis acid, while in the cyclohexene we have the addition reaction. So these two things are different. Now just look at this here. The benzene ring in fact doesn't react with the bromine or chlorine in absence of the Lewis acids. In fact, they only react with the benzene. I mean, both chlorine and bromine can react only with benzene in presence of the Lewis acid. Now, what is the role of the Lewis acid? We will be talking about this. But firstly, what about the reactivity of the different halogens? Here in this case, you can see that the reactivity rate for fluorine is more than chlorine. Chlorine is in turn more than bromine. Bromine is in turn more than iodine. So this will be quite unusual for you, because you have so far studied that the iodine is more reactive, bromine more reactive, chlorine. But here you see that a fluorine is the being more reactive towards the halogenation, for the halogenation, than the chlorine does, and then chlorine is more reactive than bromine. And then what is the role of this Lewis acid? For instance, we just talk about the bromination of benzene, where the first step is the attack of the one of the bromine molecule on the Lewis acid, because Lewis acid, as you see, is electron deficient center, the metal group. So these lone pair of electron of bromine attack on the iron, and then we will have this transition state shown by the dotted lines, and then ultimately we will have this bromonium ion formations, which is very much reactive. Bromonium ion, this benzene ring, which is a nucleophilic center, is an electron rich center, will attack its electron will flow towards bromine, where we have a carbocation, and then you can see that the flow of electrons that is moving from one side to the other side, and then we will have we are having that final product where the carbocation is now coming quite near to the carbon where the bromine is attached. So all this you can see on the slide number 7 negative that we have. So one of the bromine from there is coming, in fact that is abstracting proton from the from this intermediate, and that we have the regeneration of the double bond, and so as the aromaticity. So there is a regain of aromaticity. This is the stabilizing factor in this reaction. That's why this reaction is happening, because we have the regain of the aromaticity. in the addition reaction we lost the aromaticity, but here in the substitution reactions we regain the aromaticity. As we are talking that one of the compound FBr3, this is acting as a Lewis acid, and you can say that whenever there is a Lewis acid there should be a Lewis base. I mean, Lewis acid is an electron deficient compound, so there will be a compound that can donate its electron to the Lewis acid. So that compound can be called as a Lewis base. Here the Lewis base is the benzene by itself. Benzene donate electron, the FBr3 this accept electron. So it's a Lewis acid based reaction. Bromine molecule is non-polar A. You can see it will not react under the normal conditions unless you have this Lewis acid, because you have to generate that electrophile. Bromine, in fact, bromine molecule is a weak electrophile. So in order to polarize this to make it a good electrophile, you need to use the Lewis acid. Lewis acids will polarize this non-polar bond, and once this bimolecular bond is polarized, then it will be able being attacked by the nucleophile. That is, you can see that this is the energy profile diagram for this reaction that we have discussed. The benzene ring, you can see that we have the reactant which is at the higher energy, potential energy. That's why they are most unstable, but the product, they are at a lower energy, which means that this reaction is feasible because reactants are at a very high temperature and products are at a lower temperature. On the other side, you can see that there are two formation of the two transition state in this reaction: transition state 1 and transition state 2, T1 T2, and in between these two transition state we have the intermediate, which is the carbocation intermediate formation in this reactions, and then we have the product. So you can see the position of everything in this energy profile diagram: the reactant on the higher energy side, product on the lower energy side. There's a marginal difference of 10.8 kilocalorie energy between the position of the energy of the product to that of the reactant, and we have the intermediate in between. So you can see that so if I am asking you, the question is that can any one of you tell me what is the activation energy? What will be the activation energy? How you will draw a line to show me that represents the amount of the activation energy in this model. So I'm waiting for your response. So you didn't answer me. The answer is that you can draw the arrow from the reactant towards the first transition state. This is the amount of the activation energy required for this reaction. I mean, drawing an arrow from the reactant upward towards the first transition state. So the height of the first transition state to the reactant, this much height represents the total amount of the energy required for this reaction. We also talk about the two type of the activation energy. The first activation energy is, of course, which is also regarded as the total activation energy of this whole reaction, is in between the reactant positions to that of the first transition state. This is the total amount of energy required, or the activation energy required for this entire reaction. But on the other side, you can also say that if we for a while, if we consider this reactive intermediate as our reactant, and then measuring the height of the to the second transition state. So starting from the reactive intermediate position towards this represents another activation energy, which is now, of course, a little bit, in fact, it's quite less than the first activation energy.